Sir, you're inaudible.
All right. So computer registers are basically high-speed memories that the CPU works with, okay? High-speed memories that the CPU works with. Now, how do registers work with the CPU? Registers work with the CPU by basically, just like any other memory, by holding instructions temporarily before the CPU fetches it. Okay, so there are three different things that happen when the CPU is working with the registers. So the registers perform three different things. Number one, it fetches. So what is fetch? Fetch operation is used for taking the instructions that are given by the user and the instructions that are stored into the main memory. Okay, so the register picks the instructions that have been loaded by the user and the instructions that have been loaded into the main memory, because the main memory is a slow speed memory. The main memory, we are talking about the RAM, okay? The main memory is the RAM. So it's a slow speed memory, and therefore the fetch operation picks instructions that the user has given the computer, and also instructions that have already been loaded into the RAM, fetches them, okay? Then the registers also decode. So decoding, what is decoding? It is interpreting the instructions it has fetched, all right, and interpreting them in it's like converting those instructions to a language, or to converting the instructions to a form that the CPU can actually fetch and process. So look at this. When the CPU is fetching, I've also used the term fetch, but now I'm talking about the CPU, not the registers. When the CPU is fetching instructions from the registers, those instructions are already decoded. So they will not have to pass through here. Look at this. They will not have to pass through here. Are we together? They will not have to pass through there because they're already decoded. So they can go straight away to the arithmetic and logic units. Okay? So that is why the registers are fast or high-speed memories, because the CPU, when it picks from a register, it doesn't have to decode it. The register has already decoded that instruction for it. It has already been converted into bits, a form that the CPU can understand. So it also decodes these instructions, and then it executes. The execute operation is performed by the CPU and not the registers, the CPU itself. So there are three particular operations that are associated with the registers: fetch operation, decode operation, and execute operation. Fetch operation is basically loading into the register instructions from the RAM or instructions from the user, directly from the user, from input output, from input activities, okay, by the user. And then decoding is converting those instructions into a form the CPU can understand and execute straight away without having to decode it itself, okay? Then executing is now that is the function of the CPU. So because the register is work is basically to temporarily load, temporarily hold. And therefore now the CPU can fetch and execute, and then the results of execution and can now be stored in the memory. We are talking about the hard disk, other kinds of storage that are connected, and or they can be displayed on the monitor, or they can be displayed on a printer if it's something that is being printed, or they can be displayed on the, not displayed, but heard through the speakers, okay? So executing is basically converting instructions to meaningful information, all right? So there are basically different kind of registers. The most common registers used in a basic microcomputer like your laptop or your smartphone or your desktop PC, there are different kinds of registers that basically the works with. How many are these? Data register, address accumulator 3, instruction register 4, program counter 5, temporary register 6, input register 7, and output register 8. All right, so let's look at all of these registers. The data register is symbolized by DR. It holds the memory operand. What is an operand? An operand is basically a value that is being worked on, especially in a mathematical calculation. For instance, if you say x plus x is equals to 1, line or algebraic segment, x, y, and z are the operands. Operands are values that are being worked on in a mathematical calculation, okay? And operators are the symbols that work on those values. For instance, if you say x is equals to y plus z, equal is an operator, plus is an operator, okay? And then operands are the values. X holds operands that are being worked on. The address register holds the address, okay, for that particular, for the memory. It holds the address for the memory. In other words, you see here in this fetch operation, it can fetch an instruction from the RAM, okay? So it meaning that that instruction from the RAM came, it was not haphazardly from any part of the RAM. It came from a particular part of the RAM which had a memory address. So the address register keeps the address of the RAM address of the instruction that has been fetched. Okay. Then accumulator. Accumulator is now the register that works with the processor. Okay. It works closely with the processor, basically for loading and fetching instructions to the register into the processor. Then instruction register basically holds the instruction code. What is a code? A code is basically a bit language that basically recognizes an instruction. So every instruction has a code. That's why every instruction has to be done what? To be decoded. Okay, so the instruction register basically is responsible for together. Then the program counter holds the address of the instructions, just like which one? Address register. Okay, the program counter holds the address of the instruction. The temporary register holds temporary data. Input register carries input character. In other words, instructions from input activities by the user. Then the output register holds output characters. That is, when the processor is done processing instructions, the results of the processing are loaded back to the registers. But now to this particular register called the output register. All right. So remember these kinds of registers, okay? All right. Instructions, instruction cycle, and instruction pipelining. This is just under microprocessor organization. It's nothing. It's not a different topic. It's in the same topic. So here we want to look at instructions and how they are manipulated by the processor. Okay. Now, what is an instruction? An instruction is basically a group of bits that have to be executed by the processor. An instruction is a group of bits that have to be executed by the processor. And what makes an instruction is that after it has been processed, it leaves the system in a different state entirely before the processing happens. Are we together? It leaves the system, the computer system, in a different state entirely before the processing happened. All right. For instance, if you say there is an instruction, like if you go to a folder, you right-click the folder and you click rename in the pop-up menu that appears. Now, when you click rename and then you rename, of course, the CPU has to pick that instruction for renaming and then read the input you are giving it. Okay, read the input you are giving it, and after that is completed, then the system is left in a in another state it was not in, okay? Because now you've renamed. Now the computer has another different state. Or if you are copying a file or you are downloading a file to the hard disk from the internet to the hard disk, when that file has been successfully downloaded, you see download is an instruction that the computer was processing, okay? So after that, after processing is done, the instruction is over, then the system is left in another permanent state, in another permanently different state than it was in, which is different from what it was in previously before the instruction happened. Okay, so an instruction is basically a group of bits that are to be processed by the processor, and when they have been processed, it leaves the system in a different state from how it was before the processing occurred. Okay, so that is what an instruction is. All right, now for an instruction to be processed by the CPU, the instruction has to go through several stages, and those several stages are what we call the instruction cycle. Okay, so the instruction cycle is basically describes the stages of processing or executing an instruction, from the time the instruction begins to be executed to the time the results or the output of that instruction are given. All right, so let's look at the instruction, or before we look at the instruction cycle, let's look at the parts of an instruction. Okay, the parts of an instruction, a bit that has to be executed. What are the parts? The instruction has three different parts: the mode, operation code, and the operand or the address of the operand. These are the three parts of an instruction. The three parts of an instruction. Logically, of course, not physically. You won't see it on the screen. This basically CPU logical functions, okay? So the instruction is seen to have three parts by the CPU: the mode, the operation code, and the operand or the address of the operand. The mode field specifies how the operand will be located, where the operand will be located. So for instance, is it going to be loaded temporarily in the registers or in the cache or the RAM or the virtual memory? If we are talking about a big program, we talk about the virtual memory for temporary loading, right? So the mode field describes where that the location of that, the temporary location of that instruction. Where is that instruction going to be preloaded before it is executed by the CPU? Okay, the mode field. Then the operation code specifies the operation to be performed. Operation code is basically what the instruction is about. For instance, download is an instruction, copy is an instruction, paste is an instruction, move is an instruction, rename is an instruction, delete is an instruction, change password, when you change password, is an instruction. So basically, operation code is basically, it specifies the kind of operation to be performed, and that particular operation is read by the CPU using its code, because every instruction, can you imagine how many codes the CPU has to read? A lot, millions of operations, because every operation that the user will ever do with the computer, even the ones the user will never use, and the ones the system itself does, every bit of the operation, it has a code. So can you imagine how the computer does a lot of work, right? So the operation code is that particular part of the instruction that defines what that instruction is about. For instance, download is an instruction, and that instruction is recognized by a code, okay? And it is that code that is decoded, all right? So that the computer can know that's a download operation, okay? So operation code is that instruction, what that instruction is about. Now that's that when that instruction is executed, what operation is going to take place, okay? Then an operand, this particular part of the instruction, it contains the location of the operand, e.g. the register or the memory location. The operand, we said, is the operand is basically the values that are being worked on. Like this being added to this being added to this. You see, when every instruction that is being, when every instruction is being executed, there is a lot of mathematical calculations taking place, like amount of what is the amount of space in the hard disk, what is the amount of space in the RAM, what is the amount of space in the cache, what is the amount of space. So all those kinds of calculations that happen related to a particular instruction are stored, not really stored, but they are part of this part of the instruction called the operand, or the instruction cycle. The instruction cycle. Now, these are the stages. The instruction cycle, these are the stages that the instruction goes through from the time it is executed, from the time it is loaded to the one of the memories, whether it's the RAM cache or the registers, to the time it is done being processed by the CPU. And now it's being channeled to the output devices and the storage devices. So the instruction cycle is basically the stages of processing or an instruction. Now these are the stages. The instruction is first fetched, then decoded, then the address is read, then it executes. That's basically the stages. And you already remember this from registers. Fetch. The instruction is fetched from an input activity. The user does an input activity. For instance, I click download. That's basically an input activity I'm doing. So I've given the computer an instruction, download, right? So it fetches that instruction, then it decodes that instruction. Again, we said if it is going to be loaded to the registers, then the CPU doesn't need to decode it itself. The register will do it. But nevertheless, it will still be decoded, whether it's by the CPU or the register. There has to be a decoding, because every instruction, whether by the user, especially instruction by the users, are normally in human level language, high level language. So they have to be decoded, converted into low level language, bits and bytes. And then after that, the memory, the address of the memory is read. In other words, in which what is the address of the memory that instruction has been loaded into? Why? Because that will help the CPU to access it from that memory better, because it knows where it is, where specifically it is in that memory. And then when it fetches it from the memory, it can then execute it. Okay. So fetch, decode, read memory, read address, and execute. That's basically the instruction cycle. Okay. So remember that. Fetch, decode, read address, and execute the instruction. Execute is basically processing it, now converting it to a form that can actually be done by the computer. So when it executes download, then now I can see my file downloading. Okay, meaning that instruction has been executed. Okay. Instruction pipeline. Now there's something called pipeline processing, and pipeline processing basically occurs when we are talking about complex instructions. Okay. Complex instructions. Okay. Like we talked about the CISC. The CISC computers, the CISC processors, the Intel, the Pentiums, and the Motorola's. Now, for those kinds of processors that deal with complex instructions per given microsecond, there is what we call an instruction pipeline. Okay. Now, most of these digital computers with CISC processors require this instruction pipeline to carry out operations like fetch, decode, and execute. Normally, a processor will perform this, whether it's an RISC or a CISC, it will perform all this. Okay, all this. This is the general instruction cycle. But then when we are dealing with the CISC, it not only follows the cycle, but it follows a pipeline. Okay. And that pipeline just basically does what instructions are being done, what are being done to the instructions here. Just the same thing. It's just that it's called a pipeline because it is associated to a CISC process. So an instruction pipeline enables CISC processors to process the instructions in a better way because it is dealing with many and complex instructions. Okay. So this is the process for an instruction pipeline. We have looked at the stages of an instruction cycle. Okay. they are here. These are the stages for an instruction cycle. Now, these are the stages for an instruction pipeline. An instruction pipeline is like an instruction cycle for a CISC processor. Okay, because a CISC processor just works on you know, not a primitive, because instruction cycle is like a primitive cycle. It's a primitive way of, you know, processing instructions. But then instruction pipelining is a more developed way to processors. So look at the stages of an instruction pipeline for CISC processors: fetch, decode. Now look at how you see these ones as four fetch, decode, read the address, and then execute. Now this one, there is fetch. We've talked about fetching. Decoding, we've talked about decoding. Then it calculates the address, the effective address, the address which can hold that particular instruction, because that instruction is complex. So that instruction has to be given a particular effective address, an address that can be fetched easily, or that can be accessed easily by the CPU during processing. Then after calculating, it fetches the operands from the memory. Then after fetching the operands from the memory, it executes the instruction. Then executing is basically processing it now so that the machine can actually do something. It's download. Now you can see your file downloading. Then it stores the result in the proper place or in the proper memory. Okay. So instruction pipeline, I want you to just get the difference. Instruction pipeline is the instruction cycle of a CISC processor, because the normal instruction cycle is like a primitive way. It's like a primitive way of, processing. But then the instruction pipeline is basically a more enhanced and developed way that enables CISC processors to process the instructions better. Okay. So these are the, and you can see it's actually not a very big difference. We just added two items, number 4 and number 6. Fetching the operands and storing the results in the proper place. And storing is just after executing. Of course, for instance, let's take an activity like download. After download, that particular, the results of that instruction download after they've been executed, they have to be stored in the hard disk, in the folder that you picked. Yeah. So that's basically number 6, storing the result in the proper place. Okay. So this is what we call the instruction pipeline. Okay, instruction pipeline is basically the instruction cycle. It is a more enhanced instruction cycle specifically for CISC processors. Okay. So I want you to go and read segment 1 and segment 2. You know, all this, like go and study this diagram. This diagram just shows how the instruction pipelining works. Okay. Just study this. If you have any questions, you can actually ask so that I can explain it better. Okay. So that is what we call the instruction pipelining. I'm just trying to rush so that I can actually cover something before the next class begins. Okay. Let me confirm something here. I'm feeling like I'm giving you a lot of information in a very little time, but anyway, you'll have to bear with me because I'm just trying to rush over the content, the syllabus. So that let's look at instruction level parallelism. Instruction level parallelism. Instruction level parallelism, which is ILP, is a measure of how many operations in a computer program can be performed in parallel or at the same time. Instruction level parallelism is a measure of how many instructions can be executed at the same time. That is called instruction level parallelism. It is a measure of how many instructions can be executed at the same time. Now, instruction level parallelism, you're going to deal with, you are not going to deal with some of these, terms or some of these mathematical concepts. Instruction level parallelism, you will not have to deal with these mathematical concepts at your level, but the deal here, what you have to understand is that instruction level parallelism is basically a measure of how many instructions can be processed together, all right? Because microprocessors are multiprocessors, okay? They are multiprocessors. Like, for instance, your phone can play music, your smartphone can play music, at the same time you are typing a message, at the same time it's downloading some file, at the same time there are other programs like YouTube running in the background. You are using picture in picture, at the same time you are reading a file, so it's all microprocessors are multi-processors. They have multi-processing abilities. So basically, because of multi-processing, instruction level parallelism is a measure of how many instructions can be executed at the same time, okay, in a multi-processing environment. I don't want to go through these particular mathematical functions, okay. I don't want to go through a lot of these mathematical functions, but then we are talking basically ILP is basically a technique for just measuring how many instructions can be executed at the same time. So there are some which can execute millions of instructions at the same time. Some can execute multi-millions of instructions at the same time. That's basically instruction level parallelism. Now, what is a superscalar processor? A superscalar processor is a CPU that implements a form of parallelism called instruction level within a single processor. A superscalar processor is a processor that implements ILP within one single processor. One processor performing different activities. So because it's just one processor being shared, its CPU time is being shared between different instructions, then that particular CPU has to be divided out. The CPU time has to be divided out to the different instructions. So a superscalar processor is a CPU that basically performs it performs instruction level parallelism with one single processor. Are we together? I'm just trying to go to give you the overview because the notes are going to be there. Okay. Superscalar processors. Then there are what we call scalar processors. Scalar processors are processors that cannot perform ILP. In other words, one instruction has to be executed and that most of them are not standard modern machines. Okay, so we moved from scalar to superscalar. Your laptop is a superscalar, has a superscalar processor. Your smartphone has a superscalar processor. Basically, a superscalar processor is one that can maneuver through different instructions or different program threads, and it is just one process. So one processor can perform different instructions at the same time without having to remove one instruction. In other words, you don't have, for instance, if it is your smartphone, you don't have to close a file to open another file. You can open many files, you can open many programs that they can be running in the background. Okay, and they are being run by just one processor. So we moved from scalar to superscalar. Okay, all right. So basically, that's it about the superscalar processors. Okay, and your machine is a superscalar processor, as I've said. Okay, so A superscalar processor, in a nutshell, is a processor that can be envisioned, or it can be perceived as a processor that has multiple parallel pipelines. You remember instruction pipelining? Yeah, different instructions passing through the same pipeline or being processed at the same time. Okay, so a superscalar processor can be perceived to be a processor that has multiple parallel pipelines. You can have different instructions in different pipelines. Pipelines are virtual, they are not like pipes, okay? So they are just virtual ways of perceiving them, okay? So a superscalar processor can be perceived to be a processor that has multiple pipelines, meaning that it is a fast processor, one, and two, it can process complex instructions at the same time. Okay, but of course it has some limitations. You can see we have 6 minutes, less than 6 minutes remaining. The limitations of a superscalar processor, the available performance improvement from superscalar techniques is limited. So there are three limitations of the superscalar processors. The degree of intrinsic parallelism, or the technique of determining how many instructions can be executed internally by a CPU, requires a lot of resources from the CPU, or requires a lot of resources from the machine itself. Okay, so it kind of will take a lot of system resources in order to manage those algorithms that really make parallelism possible. Okay, so it is what? Resource intensive. That is the first thing. It is resource intensive. All right. Then number two, complexity. It is a complex. Parallelism is a complex technique, dividing the processor into different pipelines, each pipeline supporting different instructions, and all these instructions in all those pipelines are being executed at the same time. Basically, it is by nature complex and very costly. Okay, costly. We are not talking about we are not talking about the economic cost, but we are talking about the resource cost, the CPU cost, the overall cost. How much, in other words, how much should the system, you remember opportunity cost, how much should the system ignore or put to hold in order to give parallelism priority? That's what the cost is about. Okay. And also number three, the branch instruction processing. It may have some challenges, especially if some pipelines are not assigned well. Okay, it may have some challenges. There could be some challenges, especially if some pipelines are not assigned well. Anyway, that brings us to the end of microprocessor organization. I'm really sorry. I know that there are some places that have really rushed, especially hapa kwa parallelism, but I'm just trying to do that because of the syllabus. But I've given you a general overview, especially in the parallelism area, just to show you what it is, how it works, and I've shown you that parallelism works with CISC processors. Okay, and we've talked about the disadvantages of superscalar techniques or superscalar multiprocessors. So that brings us to the end of our, not our unit, but this chapter. We are remaining with one chapter, data representation and number systems, which I was asking you if you are aware, you know how to maneuver through this from algebra. Somebody said that you are taught algebra in this game. This was actually taught. But suffice it to say, I am still willing to go through with you, of course, because it's in the content. If all of you unanimously said you know this topic, you know it, then I would not have to, because it was taught. But somebody has said that they would appreciate if I could do a review. So I'm willing to do a review. I'm going to do a review on this. I'm going to show you number systems, how to convert between number systems, Boolean algebra, and those kinds of things. Okay. So that brings us to the end of our class today. So I don't want us to have a class next week. So I'm going to have you create session, especially tomorrow. Tomorrow I'm free. So if you can create a session tomorrow, we can actually go through number systems completely for 3 hours, just like a normal class, completely for 3 hours. And then that would be it for syllabus. And then I can allow you to revise. So I want to, the session is going to close after a few minutes because it's counting down. But after the session, we are going to interact in WhatsApp. There are those we have their numbers. Or you can just tell me right now. You can just tell me right now, what time are you free tomorrow? Tomorrow I'm normally free the whole day. Of course, not free like I don't have anything to do, but I don't have lessons to teach. But of course, I have other works to do, office work. But I can spare some time to actually teach you tomorrow. So are you free tomorrow? At what time are you free tomorrow? Let's agree. The session is about to close. What time are you free tomorrow? Guys, our time is about to elapse. What time are you free tomorrow? From 11. Okay, then we are going to have our class from 11. Then thanks. Have a good afternoon then. From 11 tomorrow we are meeting. Tell the rest. Have a good time.